Hello, I'm Szymon Torunczyk from the University of Warsaw, and I will present to you our work on flip breakability, which is joint work with Jan Dreyer and Nicolas Mehlmann, which will be presented at STOC24. And this work is about a combinatorial dichotomy for monadically dependent graph classes. So, as the title says, our central object of study is the notion of a monadically dependent graph class. This is a notion originating in logic, which will be defined later. And now I'd like to argue that this is an interesting notion to study, because it turns out that several notions from structural graph theory are instantiations of this notion. Tree width, nowhere denseness, clique width, and twin width can all be characterized in terms of monadic dependence. So it turns out that monadic dependence, a notion from logic, is deeply connected with structural graph theory, but it also appears to be inherently connected with algorithmic tractability. That is why we want to understand monadic dependence from the graph theoretic perspective and from the algorithmic perspective. Our main result provides several combinatorial characterizations of this notion. Let me first describe the algorithmic motivation for this work, which is the model checking problem. In the model checking problem for first-order logic, this is the decision problem where the task is to decide if a given logical structure satisfies a given formula of first-order logic. For simplicity, I will focus on graphs as structures, but other structures can also be considered. Using first-order formulas, we can ask, for instance, whether there's a clique of size 4 in the input graph, that is 4 mutually adjacent vertices, or whether there are 3 vertices whose neighborhoods include all other vertices. I believe that model checking is one of the most fundamental and important decision problems studied in theoretical computer science, and it is central in areas such as database theory and verification. For general input graphs, the model checking problem is highly intractable. For example, testing if a given input graph with n vertices contains a clique of size 4 can be done in time n to the 4 using the naive algorithm and about n cubed using the best known algorithm. Such a running time is impractical for inputs even with just 100,000 nodes. But in practice, we use heuristics which leverage the specific structural properties of the inputs, for example, that they are sparse. This is reflected in theory by the fact that for some input graphs, like planar graphs, the model checking problem becomes tractable in the sense of parameterized complexity. More precisely, every property defined by a first-order formula can be tested in linear time on all planar graphs. And the same holds for all graphs of maximum degree bounded by a fixed constant. We say that the model checking problem is fixed parameter tractable on a given graph class C if there's an algorithm which determines whether a given graph in the class satisfies a given first-order formula in time polynomial in the size of the graph, where the exponent of the polynomial is independent of the formula. For planar graphs, this exponent is equal to 1. Now, if you think that this resembles something that you've seen before about tree width, then this is spot on. Courcell's famous result says that model checking monadic second-order logic is fixed parameter tractable on every graph class of bounded tree width. MSO extends first-order logic by the ability to quantify over sets of vertices, and not just single vertices. In particular, model checking first-order logic is also fixed parameter tractable on classes of bounded tree width because it's just a weaker logic. So there are many graph classes that are tractable, such as the class of graphs with maximum degree bounded by a fixed constant, the class of planar graphs, any class of bounded tree width, even for the more powerful MSO logic, or the class of unit interval graphs, and many other classes studied in combinatorial and TCS. The big question is to characterize those graph classes for which the model checking problem is tractable. The main conjecture currently predicts that those are precisely the monadically dependent graph classes. This is a notion from model theory that we will talk about later, and the conjecture predicts that the monadically independent classes are highly intractable. In particular, the conjecture predicts that for every graph class, model checking is either tractable or is otherwise highly intractable, and there are no intermediate possibilities. This is in the spirit of the famous CSP dichotomy conjecture proved by Bulatov and by Zhuk. Let me now define the notion of monadic dependence. As I said, the notion uses logic, and our result will characterize it combinatorially. Let's first define the notion of a transduction, which is a graph operation, graph transformation, defined by a first-order formula phi with two free variables, x and y, which can use k color predicates, as well as the edge relation. So here's an example of such a formula. It says that there is a vertex z which is colored red and is adjacent both to x and both to y. So x and y have a common red neighbor. And the transformation works in 4 steps. We're given on input a graph G. Next, we color G with k colors, the colors occurring in the formula phi. Then we define a new set of edges using the formula phi. So we obtain a new graph whose edges are those pairs of vertices for which the formula phi holds. And finally, we take an induced subgraph H of the resulting graph obtained in the previous step. So let's see this on an example. Suppose the input graph is the one subdivided 6 clique. That is the clique with 6 vertices, where on every edge we place an additional subdivision vertex. Next, let's color some of the subdivision vertices red, but some of the subdivision other vertices are not colored red. Now let's apply the formula phi, creating a new set of edges consisting of those pairs of vertices which have a red common neighbor. Finally, we remove some of the vertices, obtaining an induced subgraph. And as you can see, using this formula, by appropriately coloring the subdivision vertices of the 6 clique red, we can obtain any graph on 6 vertices as a result. And moreover, using the same formula phi, we can obtain any graph with n vertices starting from the 1 subdivided n clique by appropriately coloring the vertices, the subdivision vertices red, and taking an induced subgraph. So this way we can define a quasi-order on graph classes. Say that a graph class C transduces a graph class D if there's some first-order formula phi, as in the previous slide, such that for every graph H in the class D, there is some input graph G in the class C, such that H can be obtained from G as described in the previous slide. So let's write that C is greater or equal than D in the transduction quasi-order if this holds, if C transduces D. And note that this relation is a transitive relation on graph classes, meaning it defines a quasi-order. And so we just argued that the class of 1 subdivided cliques transduces the class of all graphs, and using this is using the formula phi from the previous slide, and trivially the class of all graphs transduces any graph class using the trivial formula which leaves the edges intact. By transitivity, for example, it follows that the class of 1 subdivided cliques transduces any graph class. So it's very complicated from the perspective of transductions. Now, define the notion of monadic dependence as follows. A graph class C is monadically dependent if it does not transduce the class of all graphs. This means that the class C is strictly simpler than the class of all graphs from the perspective of first-order transductions. So the mentioned tractable graph classes, like planar graphs or graphs of maximum degree at most D or graphs of bounded tree width, are all monadically dependent. And moreover, monadically dependent classes include all nowhere dense classes, which will be defined in a moment. And more generally, all hereditary stable classes. This is a fundamental notion from model theory, and all classes of bounded twin width. I'll briefly describe the state of the art of the connection between monadic dependence and model checking. So it turns out that the notion of monadic dependence can be used to characterize the notions mentioned earlier, and moreover, monadic dependence delimits exactly the tractability frontier for the model checking problem in restricting settings. Namely, for classes that are closed under taking subgraphs, monadic dependence is exactly equivalent to nowhere denseness and to the model checking problem being tractable over the class. Similarly, for hereditary classes of ordered graphs, that is, graphs equipped with a total order on the vertex set, monadic dependence is equivalent to bounded twin width, and to tractability of the model checking problem. On the other extreme, for hereditary graph classes which are orderless, that is, they avoid a fixed half graph, monadic dependence is exactly equivalent to stability and to the model checking problem being tractable over the class. Those are prior results which provide support for what I call the model checking tractability conjecture, that for a hereditary graph class, monadic dependence is equivalent to the tractability of the model checking problem. I'll briefly recall now the notion of nowhere denseness, as it is the direct inspiration to our work. A graph class is nowhere dense if for every fixed radius r, there is some number k, such that the r subdivided clique with k vertices is not a subgraph of any graph in the class. So the r subdivided clique with k vertices is obtained from the k clique by placing r vertices on every edge. So for example, the class of planar graphs is nowhere dense, since for every radius r, we can take the same number k equals 5, as a planar graph cannot contain any subdivision of the 5 clique as a subgraph, since it avoids k5 as a topological minor. And similarly, the class of graphs with maximum degree 3, we can also take k equals 5 for every radius r, as any subdivision of k5 contains a vertex of degree 4. There are nowhere dense classes where we need to take larger and larger values of k for increasing values of r. So, as mentioned, for subgraph closed classes, monadic dependence is equivalent to nowhere denseness. And the celebrated result of Grohe, Kreutzer, and Siebert says that nowhere dense classes are tractable as far as the model checking problem is concerned. The converse implication is easy to see for subgraph closed classes under a theoretic complexity assumption. But there are many classes which are not subgraph closed and are known to be tractable. For example, the class of cliques, as a trivial example, or classes of bounded clique width. And all known such examples are monadically dependent. Here's another perspective on monadic dependence. So one can define monadic dependence for other logic, such as monadic second-order logic, by considering transductions that involve formulas from that logic. So we can define the notion of MSO monadically dependent graph classes, which are classes which do not transduce the class of all graphs using an MSO transduction. It turns out that for subgraph closed classes, MSO monadically dependence is exactly equivalent to bounded tree width. And in general, MSO monadic dependence coincides exactly with bounded clique width. As I said, subgraph closed monadically dependent classes with the usual first order transductions are precisely the nowhere dense classes. And then we have the notion of monadic dependence, which encompasses all those notions and is more general than all of them. But in brief, monadic dependence is to nowhere denseness as bounded clique width is to bounded tree width. And all those notions are variants of the notion of monadic dependence, either for the monadic second order logic or for the first order logic, and either for monotone classes or the more general hereditary classes. So monadic dependence is the most general notion, but so far it eluded combinatorial characterizations. The main results of our paper are a combinatorial characterization of monadic dependence in terms of a separation property, which is a structural result, and in terms of forbidden induced patterns. And finally, a hardness result, proving the hardness implication of the model checking tractability conjecture. I'll start with describing the separability characterization, which we call flip breakability. And to explain this notion, I will actually describe 4 variants of this condition in increasing generality. Those can be used to characterize classes of bounded tree width, of bounded clique width, nowhere dense classes, and finally, monadically dependent classes in a very uniform way. So we call the simplest property infinity deletion breakability. Intuitively, it says that every huge set of vertices contains 2 large subsets that are infinitely separated. That is, there's no path connecting the 2 sets after removing boundedly many vertices from the graph. So here's a formal definition. A graph class C is infinitely deletion breakable if there is a constant k and an unbounded function u, such that for every graph in the class and for every set of vertices w, there are 2 sets A and B whose size is at least as large as an unbounded function in the size of w, such that there exists a bounded size set of vertices of the graph such that after removing those vertices, no two vertices from A and B can be connected by a path. So here's the definition again. And as an illustration, I will argue that the class of all trees is infinity deletion breakable. We'll just need to remove one vertex, and we will be able to find sets A and B of a size of a third of the size of the given set W. This is because in every tree T, and for every set of vertices W, there's some vertex of the tree such that after removing it, no connected component contains more than a third of the vertices of W. And in fact, one can prove that a graph class is infinity deletion breakable if and only if it has bounded tree width. Now let's consider the local variant of the notion, where we require that for every fixed finite distance d, every huge set of vertices contains two large subsets that are at least d apart from each other after the removal of a bounded number of vertices. So for each finite number d, we have a separate condition analogous to the previous one, but requiring that the distance between the two sets is at least d after the removal of a bounded number of vertices where the bound may depend on the number d. And so, for example, the class of grids, which has unbounded tree width, is deletion breakable. And here we actually don't need to remove any vertices. And this is because every set of vertices in a grid contains a d-scattered set of size proportional to the size of that set divided by d squared. Now we can just split that set, that d-scattered set, into two parts, obtaining the desired sets A and B that are now d apart. And one can prove that deletion breakability is exactly equivalent to nowhere denseness, which was defined earlier. And now we want to move to the dense world and generalize from subgraph closed classes to hereditary classes, such as the class of cliques. And a common theme in the area is that removing a vertex in the sparse world is generalized in the dense setting by the operation of performing a flip between a pair of sets of vertices. So a flip of the graph is obtained by picking any two vertex sets, which may overlap, and replacing every edge between the two sets with a non-edge and vice versa. So here we see what happens with the graph, and observe that applying the same flip the second time restores the original graph. So now we take the definitions from before and replace vertex removals with flips, and we get the following definition. Say that a class is infinity flip breakable if every huge set of vertices contains two large subsets that are infinitely separated after performing a bounded number of flips. So here's the formal definition. And a k-flip of a graph G is a graph obtained by performing k flips to G. And one can prove that a graph class C is infinity flip breakable if and only if it has bounded clique width. Now, finally, we've defined the local version of the previous notion by requiring that for every fixed number d, every huge set of vertices contains two large subsets that are d-separated after performing a bounded number of flips. And here's the formal definition. The number of flips may depend on the required distance d. Here's a very simple example illustrating this notion. Imagine a graph which is obtained by stacking many half graphs on top of each other. And suppose the set W is the bottom vertices in this stack. Then any two vertices of W are at distance 2 in the graph, as we can go through a vertex in the second to bottom row. However, we can make a flip, as shown here, increasing the distance between the two halves of W to 4. And by making another flip, we can further increase this distance to 6 between the two halves of W. And so we obtained two sets A and B, subsets of W, which are large, such that after performing two flips, the distance is at least 6 between any pair of vertices from the two sets. So our main characterization says that flip breakability is equivalent to monadic dependence. And so the four variants of breakability characterize tree width, clique width, nowhere denseness, and monadic dependence depending on whether you consider vertex deletions or flips, and whether you consider infinite distance or finite distances. Now let's move to the characterization in terms of forbidden patterns. Roughly, our main result says that a class is not monadically dependent if and only if it contains arbitrarily large patterns which resemble R subdivided cliques up to flips. And more precisely, here are the patterns. There are actually 4 families of forbidden patterns. The first family is the family of R subdivided bicliques. That is, there are 2 sets of size n on the top and on the bottom, and n square internally vertex disjoint paths with R internal vertices connecting all pairs of vertices from those 2 sets. That's the first family. The second family is similar, but we additionally form cliques on the neighborhoods of the vertices on the top and on the bottom. And the third family is also obtained from the first one by connecting each vertex in the top row with all vertices in the second row to the right of it, and similarly for the bottom row. And finally, there's one exceptional family consisting of so-called comparability grids. So n square many vertices connected as drawn here. And our main result in terms of forbidden patterns says that a hereditary graph class is not monadically dependent if and only if there are some numbers R and K such that the class contains some k-flipped R pattern of arbitrary large order, n. Or it contains the class of all comparability grids. As a corollary, we get that if a hereditary graph class is not monadically dependent, then first-order model checking is hard on that class. Essentially, we verify that each of the classes of forbidden patterns allows to represent all graphs in a way which can be easily decoded by a first-order formula. And this implies the hardness part of the model checking tractability conjecture. Altogether, our main result states the equivalence of 3 conditions: monadic dependence, flip breakability, and avoiding certain patterns. Now here's a very brief sketch of the proof. We're given a graph G and a vertex set W. And the idea is to construct a structure, which we call an insulator, around a large subset W prime of W, which is a grid-like structure of a certain height D, where the vertices of W prime are placed in the bottom row and the adjacencies between any 2 rows are well controlled. And we try to grow such an insulator row by row, each time extracting a smaller subset of the set in the base row using Ramsey's theorem. Once we achieve the target height D, we split the base set into 2 halves and obtain 2 sets A and B, which are D apart in some flip of our graph. Now, if we fail to grow the insulator by an additional row at some point in this process, it is because we can find vertices outside of the current insulator, which have a certain connection towards the vertices inside the insulator. And this connection is quite specific. And this gives us a certain structure out of which we can extract one of our forbidden patterns using, again, Ramsey's theorem. At the level of graph classes, we conclude that for a given graph class, either we can construct insulators of arbitrarily large height, which implies that the class is flip breakable, and this easily implies that the class is monadically dependent. And in this last implication, we use the locality property of first-order logic. Otherwise, we can find large patterns in the class, which easily implies that the class is not monadically dependent. And all in all, this proves the equivalence of monadic dependence and flip breakability and avoiding large patterns. So here's a summary of the current knowledge regarding the model checking problem. For subgraph closed classes, monadic dependence corresponds to nowhere denseness and to tractability. For hereditary classes of ordered graphs, monadic dependence corresponds to bounded twin width and to tractability. For hereditary orderless graph classes, monadic dependence corresponds to stability and to tractability. Those are all previous results. And finally, due to our results, for all hereditary graph classes, we showed that monadic dependence is characterized in terms of a separation property and in terms of avoiding certain patterns. And classes which are not monadically dependent are not tractable, and the converse implication remains open. And we hope that the notion of flip breakability will enable progress in that direction. Thank you for your attention.